we need to give full voice to some of these acid-catalyzed processes that are encountered around acid derivatives. So we've seen plenty of acid-catalyzed processes. Oops, catalyzed. One example would be making ketals. So we saw we could take ketones and treat them with excess alcohol. And of course, I always love going to methanol because it's quick to write, but you can use other alcohols. And a catalytic amount of sulfuric acid, just a pinch. And we will form a ketal. If we started with an aldehyde, we form an acetal. And we liberate one equivalent of water. Now, this reaction, we've seen it before. It's a reversible reaction. And this so it's in equilibrium. And the equilibrium is typically controlled by water. So if we want the reaction to go forward as drawn, we'd oftentimes do things like remove water as it forms in the reaction, or use a really big excess of methanol to help drive the reaction to the right. If we want the reaction to go backwards, we add more water. So, we're using, this is an equilibrium reaction, we're using Le Chatelier's principle to push the reaction in the direction we want. Okay, great. Very exciting. Now, how does this apply to acid derivatives? For acid derivatives, when we first encountered these, I'm going to draw this structure as an acid derivative. And Y is sort of a wild card that chemists sometimes use to denote an electronegative atom that may or may not be a halogen. So Y for us could be something like an OR group. This would be an ester. It could be an NR kind of group, and that would be an amide. Y could be a halide. That'd be an acid chloride. But you take any acid derivative and you cook it up with water and a strong acid, like sulfuric acid, could be HCl, and what you will get is the carboxylic acid plus your protonated Y group. So if it's an ester, that would be an alcohol. If it was an amide, you'd form an amine. So we can hydrolyze any acid derivative. All acid derivatives, they will all undergo this acid-catalyzed hydrolysis process. And so this is an acid-mediated reaction, and it's actually very, very much like this top reaction in how we made ketals. A lot of the electron pushing is identical. There's one other thing I want to throw at the bottom of the slide, and that is, let's not forget when we talk about acid derivatives, nitriles. Nitriles are a commonly encountered acid derivative. They don't look like an acid derivative because they don't have a ketone, or a carbonyl, but they are still an acid derivative because you have 3 bonds for this carbon to an electronegative atom. No surprise, if we take a nitrile and we treat it with acid and water, just like any proper acid derivative, it'll form a carboxylic acid. So we need to talk about this mechanism and just learn some of the language around these types of reactions.